Hi, in this video, we want to take a look at exploring missing values in our data, and we're going to be using the mice package to accomplish this. The mice package is a very powerful, very robust package for handling missing values. It has a lot of options for imputing, that is, replacing missing values with surrogate data. Now, we're not going to talk about actual imputation here. We're only going to look at ways to look at our data, get more information about our missing values so that we can make better informed decisions when we go to impute. Right. Now, much of this information is taken from amices.org, and here is the citation information for the mice package. So mice stands for multivariate imputation chained equations. But for this purpose, we don't really worry about that. What we really care about is just looking at what we have, and we want to gain insight into what's going on, because we need to have insight into our data before we can make the best choices for imputation. Now, if I'm under the gun, I'm under pressure to produce a model, and I don't have time to do it, to explore my missing values, this is a step I'm probably going to end up skipping. And I'm just going to automate the imputation process with a imputation function that I feel comfortable using. But, of course, it's best to do this if we have that luxury. All right, so let's go ahead and load our data. Now here I'm going to be, because of how the width of some printout in this video, I'm using print R to make it so that the printouts are a little bit easier to look at in the R Markdown file that I created, this HTML file. Now, here I'm changing the options to digits equals 2, just so that just to truncate things, a little bit easier to see. And we're loading the data. I'm using the read R version of read CSV. And you'll notice that I need to specify what column types are. If I don't specify, it'll make a guess for us, but a lot of times numbers like social security numbers will be treated as numbers instead of characters or factors, however we want to have it. And I don't like tibbles, so I'm using as.data frame to convert it to a regular R data frame. Now here I am cleaning up the column names just so it's a little bit easier to look at, easier to read. That's all the string manipulation is. And I'm getting rid of some useless columns on this step. And then here, I sort my data, rows and columns, by the class, and then by the number of missing values. And so why do I do that? So I find that, so when we go through and we do imputation, one thing that we will do frequently is that we'll impute, depending on our method, so the method is important, but we'll impute the ones that have fewer missing values first, and then hit the ones that have more missing values later, hoping that the filled in columns help improve the imputation on the ones that have a lot of missing values. Also, by organizing the rows and columns, this is something that makes it easier for me to interpret what's going on when I'm trying to look at subpopulations. It just makes the missing value patterns more organized, easier for humans to interpret. All right, so let's load the mice package. Now you'll notice that we have a filter function in stats and in mice, and we have base functions for cbind, rbind in both base and in mice. So if I want to use those functions, I need to be mindful which package I'm calling, otherwise I get package confusion. All right, so now let's actually get to the part that we're interested in. All right, what I want to do, I want to display the missing value patterns. All right, so what's going on here is it takes all of my missing value patterns. So a missing value pattern is a binary vector where I have a 1 if it's missing, 0 if it's not a missing value. And then what we do, we take the unique rows and the unique columns. So we're reducing it down to just the patterns themselves, because if it's not unique, then it's redundant, right? And so, or it's a repetition. And this way I can go through and I can just see what are the patterns that I'm looking at. All right, so here, there are 0 missing values in this pattern, in this row of data. And we see that this pattern appears, this row pattern appears twice. This row pattern has one missing value, and there are just under 24,000 observations with only missing suite condo. Now, if I look over here, half bath and suite condo are the only two missing values in this row. There's only two missing values, and this pattern appears 117 times. And I can go down the list until I get down to here. We have 157 observations with this missing value pattern, row missing value pattern like this. And we can see that a lot of the data is missing in that. Okay. And here it's getting obscured. I couldn't solve this overlapping number part, so I just left it. But you know, if I could read that number, it would tell me how many times. It's what, 21 missing values on this. Now, here is the number of missing values each time, and here is the column name. Now, something to be mindful of is that we can have repetitive missing value columns. You notice that all these columns have the same missing value pattern of none. Well, these two columns have the same missing value pattern of missing 2. All right, so now I kind of have an idea of what's going on. And when I do this, the system automatically prints out the missing value patterns of the columns. And it's a little bit ugly to read in R session, and using the print R package, it cleaned up what it looks like. If I scrolled over, I can see the full details, see everything. And everything just corresponds to that picture. The difference is 1 means it's not missing, 0 means it is missing. So it's the opposite of how I personally define missing value patterns. Yeah, and so something that is nice, since I went through and I sorted the columns by the number of missing, I know that this one has the most missing values. And so if I ever get stuck, ever get lost, I have trouble interpreting what's going on, I know that I have my columns partially ordered by the number of missing values. That helps me interpret what's going on as I work through this. All right, well, let's keep moving on. All right, so now the next thing we want to consider is like paired variables missing values. Or so previously we looked at univariate, 1 column at a time missing values. Now we want to look at pairwise. If I take 2 columns, put them together, what are my missing value patterns? So I could have non-missing, non-missing. I could have missing, non-missing, non-missing, missing, or missing, missing. So there's 4 possibilities. Okay, and so what we're going to do, we're going to use the MD pairs to extract the counts for this. So what's going to end up happening is that this is going to generate 4 different matrices of counts. And in a way, it's going to be kind of similar to a correlation matrix, but it's not a correlation matrix, but it's going to be similar in that manner that each variable has its own row, each variable has its own column. Okay. Now, the notation in MD pairs is RR is response, so that means non-missing. M means missing, so RM means non-missing, missing. MR is missing, non-missing, and then MM is missing, missing. All right, and for the example, I'm going to print out just the first one. I'm not going to print out all of them, but it's just going to be the counts over for each of these. And so here we can see that when we put them together, we can see the number of times that we have non-missing, non-missing in both of them. So if I take, let's say, parcel ID and address, we can see that over 26,000 times parcel ID and address are both non-missing. I'm going to keep on going. And if I keep on going, I can see that parcel ID, and suite condo are non-missing, both of them, just over 6,000 times. And so, if I want to, I can inspect this individually. Now, you'll notice that there's repetitions. Like these numbers, I see the same numbers over and over and over. Why is that? When I go back up here and I look at my columns, I see that my columns are the same a bunch of times. So all of these columns in this visualization are the same. So all of these data vectors have the same missing value patterns. All right, and so I'm going to see the same numbers over and over and over when they're paired. And so over here, we have a missing value pattern. So there's 2 columns with that. So because of the redundancies, I'm going to see the same numbers over and over and over. All right, so there's enough in here that I feel like, what we should do? We should just go in and do a heat map to kind of see like what are the groupings together. And so we know that like suite condo, it has a lot of missing values. Here, the matrix we're working with is counting the non-missing pairs, so non-missing, non-missing. And so we can see that that's going to be, yellow is going to be a smaller number, while purple is going to be a greater number. Actually, let me back that up. Address. Yeah, so here the lighter green are going to be larger on this. All right. And we can look and see this is clustering on the columns and this is clustering on the rows, and it's going to be the same because it's a symmetric matrix. Scroll down. Now we're going to look at non-missing, missing pairs. And here we get our heat map, and we kind of see like a block formation. If I go through and I scrutinize the arrangement of this, I'll see very different values. I'll see that it's a different ordering because the clustering has changed. I played around with different versions of hierarchical clustering. I didn't really see a lot of value in changing the HClust method. I believe the default for this is complete linkage. But even with single or with Ward D, which are like 2 extremely different ones, I didn't see much informative difference between them. But it's good to see kind of like how they are grouping up, how are they being paired together. And now here we're going to look at missing, non-missing pairs. Check out that big old section. And you notice that when it's flat, that's because they all have the same like values. And now we're looking at missing, missing. All right, now the next function in the mice package that will be useful is the complete cases function. So CC means complete cases. What this does is takes a data frame and this gets rid of anything that has one or any rows. It gets rid of any row that has 1 or more missing values and kicks them out. All right. I believe in base R, it's complete.cases is a corresponding function. That might be an indicator, a logical one. If I want the logical indicator, I want complete cases indicator in the mice package. And so here, this is a pretty long logical vector. So I went ahead and just passed it into table. And we can see that only two observations are complete in terms of rows. So the vast majority of my data is missing 1 or more values. Now, if I want to select only the incomplete cases, instead of CC, I go IC. So here, this function goes through and grabs all of the rows of data that are missing 1 or more values. And as we see, that's over 56,000 observations. So I'm just printing up the head of it. I'm not going to print the whole thing. It's just too much. And we can get a logical vector to indicate if we have incomplete cases. So incomplete case indicator, and it's the the negation of true false from the previous indicator. So twice we have 2 non-incomplete cases, so that's 2 complete cases, and the vast majority are missing 1 or more. All right, well, we can also calculate the number of complete cases, which is n complete cases. So we know it's just 2. And we can calculate the number of incomplete cases. Same number coming up over and over and over. So these different functions just present different things. They have different utility depending on what I'm attempting to do at a particular time. Now, when I go through and I do imputation, what I have to do, I have to decide, like, what is the relationship between the variables? If I want to start really getting into more sensitive, more specific, more tailored imputation, I don't just throw them all my variables into one model and run them and let it go. I consider the relationship between different variables. So, I consider the value of the variables. I consider the range of the variables. I consider the missingness of the vectors. And so what I can do, I can tailor things very precisely. Well, something that will make my life easier is if I was able to just let mice handle this for me. Now, mice gives me 3 options for taking care of this for me. First one is scatter. Next one is collect. Next one is void. All right, scatter. What this does, scatter means, everything's all dispersed. So this is basically having things individually by themselves for imputation. Collect means everything gets thrown into one specific model. You collect all the variables together and you put it into one joint model for imputation. And then void is like giving me empty feedback, giving me nothing. It's basically a placeholder for other things I might be doing if I'm doing things programmatically. All right, so scatter is for creating imputation model based on fully conditional specification. Each column gets its own block. And then collect gathers all variables to be imputed in one big joint model. All variables are in one block. Okay. When I talk about block, that is the variables that are used for imputing together. And then, void is one that is just we're just skipping imputation of all of the variables. And that's just there really for programmatic purposes. If I'm going through and I'm automating a process, and I can set void as an option when I see that I don't want to impute. All right, so any variable not listed will not be imputed. And variable can be in multiple blocks. A variable will be re-imputed in each block. So the final imputation for the variable will come from the last block that was executed. So order matters. The last one is the one that we want to worry about. And so the reason why this might be important is that I know that this one variable is informative to this variable, formative to this variable, and formative to this variable. But when it comes down to imputation on that one up top, I can only impute it once. And so the last one is the one that is going to be kept. All right, so if I want to make blocks, so here this is a function within mice that goes through and makes the blocks for us so that we don't have that it'll automate it. Now, in the make blocks function, what I'm doing is I'm going on the extreme cases. I'm not specifying anything. I'm just saying I want one of the 2 extremes, either scatter or collect. And so they're so extreme that R just knows to do, either it's doing everything with its own block or it's dumping them all into one individual block. And so I don't need to specify anything. If I want something more tailored, I have to roll up my sleeves and start digging in. All right, now the NIMP function counts the number of times that you're going to be doing imputation, the number of individual imputations in a block if I go about this manner. All right, so what I've done here is the make blocks function is inside and is being used to create a list. So I've got a list of 3 different make block outputs. And then I'm going to go, so what this does, this figures out the blocks and this sets up the which values are going to be imputed and which variables are going to be used or potentially used for the imputation, depending on the model that I use. This function, the NIMP function, this takes the number of imputations within each individual block. All right, so this function, I have to have a block and I have to have missing value data pass through. Now scatter, remember each one gets its own block, so I can see individually how many are going to be imputed in each individual column. For collect, everything is put together. So this is the total number of imputations that I will be executing if I fill in all the missing values of my data. And then void is just there to be a placeholder, really. Skipping imputation of everything. All right, now the next thing we want to think about is the fraction of incomplete cases among cases with observations. All right, so the fraction of incomplete cases among cases with observations, we're going to call that FICO. And so it's a fraction of incomplete cases. Because of rounding, it's just making it look like it's just one. And so remember, incomplete cases, for us, there were only 2 non-incomplete cases. So like virtually any rounding I do, it's going to make it look like 1. So I'm suppressing the actual numbers. If I was to increase the number of digits on the display, you could see more nuanced information, but it's practically 1. Now, influx and outflux. All right, the goal of influx and outflux is to try and figure out, if I look at pairs of variables, potentially, how good is this vector going to be for imputing other vectors? Also, how good are other vectors for imputing this individual one? Or if I'm interested in imputing the vector at hand, then that is the influx. So if I want to, if I take a vector, I compute its influx, I'm trying to figure out what is the potential for imputing on that vector with the other vectors. Outflux, if I take a vector, I compute the outflux, I'm looking at what does it look like the utility of that vector for imputing other vectors. All right, so in means I am imputing the one that I'm holding on to, and out means that we're imputing other vectors. And so the, what is it, flux. Mice calls it flux. P-obs is the proportion of observed values. Influx is our measurement of how well we can impute that vector. Outflux is our measurement of how well that vector can impute other vectors. And then here we have the average inbound statistic, average outbound statistic, and then the FICO, which we talked about a moment ago. All right, so influx is equal to the number of variable pairs with missing and observed, where the one I'm interested in is the one with the missings, divided by the total number of observed data cells. All right, so if influx is completely observed, then it's going to be equal to 0, where if it's completely missing, it's equal to 1. All right, and for 2 variables with the same proportion of missing data, the variable with a higher influx is better connected to the observed data, which means that it's going to be a better one to be imputed. Now, outflux. So outflux is equal to the number of variable pairs with observed and the other one missing divided by the total number of incomplete data cells. Outflux is an indicator of potential usefulness for imputing other variables. That's important. So here, outflux is for imputing other variables. And of course, outflux depends on the proportion of missing data. If completely observed, we have outflux of 1. And if it's completely missing, it is 0. And for 2 variables having the same proportion of missing data, the variable with a higher outflux is better connected to the missing data. So it would be the better one for imputing other columns. And if I use flux, this gives me the output. So this gives me some statistics about the utility. Now, something I did, remember, I sorted all my columns by the number of missing values. So I can see pretty easily that there's a trend going through all of these. So average inbound, average outbound, FICO, influx, outflux. These three are the ones that are going to be the most important for us. And if we look through, we can see that it's not, the proportion of missing is not perfectly monotone with influx, outflux. Somewhere in here, there's an example. Yeah, so we can see that here it's decreasing, 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 and then it pops up here. It increases. So it's not perfectly it's not perfect Spearman correlation between proportion of observations and influx outflux, but it's, you know, we can see that there is a relationship there. Now, why is this important? Well, so if I'm going to be going through and imputing a column, I know that these with outflux of 1 are going to be good choices for imputing other variables. Now, this is something that is just going strictly off the missingness. This is not telling me anything about the quality of the relationship between the data. That is a subject matter knowledge aspect. If I know that there is a relationship, otherwise, so let's say like sales price and land value, we know that those two are going to be highly correlated. I might want to ignore these statistics for my imputation process if I know that there are variables that are more informative towards each other, even though I don't have the full missingness I would like. What I could do, I could impute with the ones that subject matter wise I know are better. Then I go to the ones that are weaker but have better outflux statistics. And remember, for a lot of machine learning models, what we have to do, we have to get rid of all missing values. We have to impute everything. So either I have to throw out an observation or I have to impute it. This includes neural networks and linear models, generalized linear models also. And so if I have any missing values in the variables that are used in the model, then that entire row gets kicked out. In this data set, you can see that we'd be down to two observations if I didn't impute or reduce down the variables. Now here, this is supposed to be a scatter plot showing the influx, outflux. So influx is along the x-axis, outflux is along the y-axis. So if it's over here, it's better for being imputed. And if it's over here, it's better for doing the imputation on others. Now remember, this is only talking about the missing value aspect, the missingness. There is no consideration of the subject matter knowledge or the statistical relationship between the variables. I have to use my knowledge of what's going on for that to happen. All right, and just let you know, a squirrel went just sprinting by on my fence. I hope everything's okay, but it distracted me, it surprised me. But I hope everything is, oh, and okay, so why do we have the overlap? We have the overlap because when I look at my influx, outflux statistics, I see that I've got repeat values. And so when this gets plotted, they get stacked on top of each other. And so it's hard to read. But we know roughly where things are. Well, that's all I've got for you. Take care and goodbye.